Let's get started. Okay, so today's afternoon lecture is about cost semantics. So what we've done so far over the course of the last few days is to try to give you a handle on the basic ingredients that tell you, command from this morning, what programs are and how to reason about them. And we've gotten some pretty sophisticated stuff going in terms of observational equivalence and logical equivalence and parametricity for all and exists. And that will all get extended later in the summer school to techniques for reasoning about imperative programs and techniques for reasoning about recursive types, which is the kind of thing we've been doing with building up observational equivalence and logical equivalence on steroids to account for these programs that are now harder to reason about. Okay? But one thing we really haven't talked about yet, this will be another thing that comes back later in the summer school, is kind of the question of efficiency, or how long do they take to run? Right? So we haven't really talked yet about tools for reasoning about not what does this compute, but how long will it take to get there? Okay? And that's this idea of cost semantics that I want to broach today. And the big picture here is really a nice idea that I think is kind of just a general idea that's a template for a lot of different research, which is what we want to do with cost semantics is to take a high-level language with, features like these and the kinds we've been talking about, and then in terms of making it feasible to program, we take our high-level language and then we compile it to some sort of machine on which we actually execute the high-level programs. And one of the things that'll come back later in the summer school is the idea of what does it mean for this high-level language to compile correctly to this machine. So at a very, very simple level, it's something like if you have a program that runs like that, then you have some compilation of the program, all right, with the dagger sign that was used in the hands-on session problem from yesterday for compiling dynamic typing, but the idea is somehow it should be the case that you take your program, you compile it, and that runs the same after compilation as it ran before. And of course, this is, let me put scare quotes around that because that's a very, very simplistic way of thinking about things. You really need to get more sophisticated stuff going to really talk about compiling a functional program into assembly code and what's the spec for actually saying that it runs the same. But what we want to do today is to start to think about how we play the same game with cost. So when you run a program on a machine, there's some concrete cost to executing that program, right? You can look at your watch and be like, it took 7 seconds, or you can count the number of machine instructions or the number of memory accesses or something like that, right? There's things that depend on the particular features of the machine that you can count. But in order to think about programming and programs, just like we don't want to actually write assembly code all the time, we want to write in a high-level language. When we reason, we don't want to reason about the compilation down to assembly code. We want to reason about a high-level semantics that's preserved by compilation. What we would like is the idea that there's some abstract notion of cost that is preserved by the compilation in the sense that the abstract predicts in some way the concrete costs. And in a very loose sense, which probably could be made precise, but I haven't really thought about that, you can think of this as some kind of functor, right? Because we're saying we're taking the objects, that is the programs, and mapping them from the abstract land, the high-level land, to the concrete land in such a way that the maps between them, right, I mean, this is kind of precise, are preserved. And then in a way that we'll see, this is kind of some sort of additional preservation property. And to make that precise, you would have to sort of, like, I think this could be made precise, but I just mean it in a hand-wavy sense that we're talking about maps between languages that preserve stuff. And the idea is we should have abstract stuff that gets preserved in some appropriate sense for talking about the concrete stuff. Okay, so the particular example I want to do for today, I mean, this is a general thing, and you might have different notions that go into your concrete cost, like how many processors do you have, or what your cache architecture looks like, or various things like that. The example that I want to talk about today is specifically cost semantics for parallelism, because that's one spot where there's some nice things to be said. So the idea here is that we're going to assume that we have the concrete ability to compute simultaneously. So for some reason, our machine that we want on that side can do many things at once. And this is, of course, an important thing these days because of things like multi-core and programming GPUs and programming data centers and things like that. And so it's a good thing to study. And then the idea is that the high-level language will just be functional programming in this, or maybe those plus this kind of fragment of the world. So what we want to think about is functional programs in the absence of the kind of imperative programming that Bob introduced this morning, or just sitting in the kind of functional level that sits above the command language that Bob was talking about this morning. So the idea is that if we're not talking about executing commands that modify memory, then functional programs are parallel programs in a sense that we'll make precise in a second. Okay? So we're going to talk about executing functional programs in parallel. So let's see what that looks like. And then the game is, okay, so like big picture, we're going to talk about this as our high-level language. And then eventually we'll get down to thinking about how some abstract costs that we can identify for our high-level language map to concrete costs. Yesterday, we had the rules for pair types on the board. E1, E2 has type tau1 cross tau2 if E1 tau1 and E2 tau2. And if you remember what we said about the dynamic semantics, it was that E1, E2 steps to E1 prime E2 if E1 steps to E1 prime, and if E1 is a value and E2 steps to E2 prime, then E1, E2 steps to E1, E2 prime, and then when they're both done, it's a value. Okay? So I'm going to write sequential today on that operational semantics from yesterday. And I'm going to contrast it with what I'll call the parallel computation steps. And to think of a functional program as a parallel program, there's really not that much we need to do. Here, what did we say for running a pair? We said, if you're going to run a pair, first you step the left-hand side until it's a value. Then you step the right-hand side until it's a value. But if we're in the setting of pure, in the sense of no commands, or no commands that we're running right now, functional programming, is there any dependence of the evaluation of E1 on the evaluation of E2, or the evaluation of E2 on the evaluation of E1? No, because the way in which we step E2, having stepped E1, is exactly how we would have stepped E2 before we stepped E1, right? They're just two independent mathematical expressions, maybe expressions involving non-termination or something like that. So it's, a funny kind of math, but they're totally independent. So the idea with parallel computation is simply this. We'll have E1, E2 steps to E1 prime, E2 prime, if E1 steps to E1 prime and E2 steps to E2 prime. Okay? So for parallel evaluation of a pair, what we say is, instead of saying, first you run the left, then you run the right, we just say, you can run both of them at once. Okay. So for example, if we had 1 plus 2 comma 3, or let's do, 1 plus 2 comma 3 plus 4, then if we're executing it sequentially, it would take a step to 3, comma 3 plus 4, and then take a step to 3, comma 7. But if we're stepping in parallel, then we would go to 3, 7 in one step. Okay? And just as a little bit of a technical device, so in this case, I could step both components, right? So with the rule I've stated, it says you positively must step both components. But if you had something like 1 plus 2 comma, 7 that you wanted to run, then in that case, one side takes less time than the other because one side's already a value and one side still needs to take a step. So I'm going to put a little question mark on these. This could be just spelled out as like 4 different step rules, where the E parallel stepping to E prime question mark has 2 rules. Either E parallel steps to E prime, or if E is done, and then E parallel steps question mark to itself. Okay? So the idea of the question mark step is just a little auxiliary judgment that says, if you're already done, then you're allowed to stand still here. If you're still going, then you have to keep going. And then there'll be an additional constraint here, just because I want this to mean somebody actually took a step, which means that they're not both constructed out of that rule. Okay, like this can easily just be spelled out as you just have 4 rules where one of them says they both step, or 3 rules. One of them says they both step, one of them says one steps, one of them says the other steps. But I just want to kind of compactify that with that notation. Okay, good on that? Okay, so in what sense is this defining, so what does this mean now if we have this idea? What this means is that in a parallel step, when you say that E parallel steps to E prime, you can do an arbitrary number of parallel steps of computation. Right? So if I had something like 1 plus 2, comma 3 plus 4, comma 5 plus 6, then because that's a nested parallel step and that's a nested parallel step, I could, in one parallel step, get right to 3, 7, 11. Okay? So we're sort of allowing unbounded amount of parallelism at once. We're just saying whenever you have independent sub-expressions, then you can run the pieces of them in parallel. Okay? So this is kind of a notion of parallel stepping. And now the question is, in what sense are we still running the same functional programs? Well, the sense in which we're still running the same functional programs is that there's a theorem which says that what we're doing is deterministic parallelism. In particular, E steps in some number of sequential steps to V if and only if, something we haven't talked about yet, if and only if E steps in some number of parallel steps to V. Okay? So if you leave out the middle thing, which will be a helpful bridge between those two, what the deterministic parallelism theorem says is that we're running the same program and getting the same answer, right? We get the same answer, just potentially faster. Okay? So for now, let's just say that the pairs are only parallelism construct. So you could extend this so basically you have some choices here. So in the book, what Bob does is he introduces a new form of parallel let that is the source of parallelism, and then pairs themselves are not parallel. Another way to do it is you could sort of make the pairing constructor parallel, make function application parallel. It's kind of like up for grabs exactly how you want to integrate it. I'm just going to do this just because it's the simplest thing to write on the board today. But the idea here is that if I write a function like to merge sort a list, what I do is I split it into two sublists, P1 and P2, of roughly equal size, and then I merge together the results of merge sorting the left and merge sorting the right. Right, so like just think of some divide and conquer algorithm or something like that. Then the idea is that if those parentheses mean parallel evaluation, then just by writing this code as a functional program, I've expressed some parallel computation. Okay? And the parallelism that I've expressed, what the parallel evaluation expresses, is sort of what are the dependencies in the computation. So if you look at a rule like something like gamma proves let xy be E1 in E2 has type sigma if E1 has tau1 cross tau2, and assuming x stands for the first part and y stands for the second part, E2 has sigma, something like that, then would you expect that let or open or split or whatever you want to call it, a limb for pairs, to execute this and this in parallel? No, right? Because somehow we never are supposed to run the branch body of a let until we've actually computed the thing that goes in for the variables, right? We don't run open code. So this is expressing a dependence of I don't run E2 until I've run E1. Okay, so the rules for this would be the same sort of thing, where it says let x, y equals E1 in E2 will step in parallel to let x, y be E1 prime in E2 if E1 steps in parallel evaluation to E1 prime. Okay, but you won't have the rule that would like go into E2 or something like that. That is, some constructs of a functional programming language are naturally sequential because it says do this, then do that. It's sort of a let or sequencing. Some things are naturally parallel, like pairs. And the deterministic parallelism theorem says that you get the same answer no matter way. Okay? You get the same answer either way. So let's look at a little bit of how you prove this. So this relation that kind of sits in the middle is what's called, you should see this sometime, you can read about it in Bob's textbook, is called, sometimes called big step or an evaluation semantics or something like that. And the idea is that what we would say in this case is that if E1 evaluates to V1 and E2 evaluates to V2, then the pair E1, E2 evaluates to V1, V2. Okay, so the idea is that whereas the stepping rules tell you how to make progress on one step of computation, right? The stepping rules tell you here what one step of computation is. This tells you what one step of potentially parallel computation is. The evaluation relation or big step semantics tell you how to run a program all the way down to a value. So to run E1, E2 all the way down to a value, I run E1 down to a value, and I run E2 down to a value. Okay? And as a technical device, it helps to match up this with this and this with this. Matching up this with this is kind of a standard first exercise in understanding evaluation relation semantics. You just do it by induction. And you'll get a flavor for that since I'll do a little bit of this correspondence. Okay, so how does this work? Let's do the from which one do I want to do? Let's do the from if E evaluates to V, then E steps in many parallel steps to V direction first. Okay? So how do you do this proof? Well, you've got an inductively defined evaluation relation. It's got rules like that one. The proof is by induction on that gadget. And so, for example, we'll have a case for if E1 evaluates to V1 and E2 evaluates to V2, then E1, E2 evaluates to the pair V1, V2. Okay? So what do we get by our inductive hypotheses? E1 steps in many steps to V1. E2 steps in many parallel steps to V2. Okay? And what do we want to show? We want to show that the pair E1, E2 steps in many parallel steps to the pair V1, V2. Okay? So how do we do that? Well, what does this look like? This looks like E1 steps to E1 prime, steps to E1 double prime, steps to E1 triple prime, and then eventually hits V1. This looks like E2 steps to E2 prime, steps to E2 double prime, and then eventually hits V2. And what do we want here? So what do we do here? Right? We just match them up and say, well, we can do that, and then we can do E1 double prime, E2 double prime. Then what's going to happen eventually? We'll hit some spot where, let's say, E1 is still in the middle of what it's doing, but we've already hit V2. If, for example, V2 takes fewer steps than E1. And so then we'll keep going with one more prime on E1 there, holding V2 still, and then eventually we'll get to V1, V2. Okay? So because we don't know that the two things take exactly the same number of steps, one of them will finish first, then we just stand still on the other side, and then use that fact, I guess the rule's gone now, but use the fact that we can stand still in one side or the other. Okay? So what are we doing? We're saying this one runs in some number of steps, this one runs in some number of steps. We will keep going like that until one of them is done. So if this takes, let's say, n1 steps, and this takes n2 steps, then overall, what did we take here? In general, the max of n1 and n2, because we don't know which is bigger. Okay? Good? Okay, and then we can do the converse. Let me think for a second about whether... Yeah, I don't think the converse really, yeah. So to do the converse, I'll just tell you the trick for setting it up, and then you can work it out yourself. So what we want to prove is if E evaluates in many steps to V, and then E evaluates to V in that sense, what does many step really mean? It means either you took 0 steps, or maybe 1 step, or you took a step and then you took many more steps. Okay? So what you do first is an induction on the length of the star. And then the inductive step, the interesting thing, is showing if E steps in parallel to E prime and E prime evaluates to V, then E evaluates to V. i.e., what are we showing? That evaluation is closed under converse. Evaluation in this evaluation relation sense is closed under converse stepping in the sense that we talked about with the logical relation stuff earlier in the week. Okay? And so that you can do by induction on this, and you just spell out the cases, and it's not too bad. Okay, good? So now what we've got is the idea that this parallel evaluation, right, the theorem now says that this parallel evaluation holds if and only if that middle thing does, if and only if that does, which justifies the idea that what we're really talking about is running the same program to get the same answer. We're just doing it faster, right? Okay, good. So, good. Keep that. All right. So now I want to introduce the idea of cost semantics, which we've kind of already introduced, but not quite. So given a closed program E, there are two things we could count. Right? What we could count is the star on that and the star on that. Because by that theorem, we know that given any closed program E, if it has a value, it's going to step to that value under both notions of semantics. But the idea that we're getting the same answer just potentially faster is sort of saying we could count how many steps does it take for that one versus how many steps does it take for that one. And this one I'm going to write as a W, and that one as an S, because the terms that get used for these in the parallel programming literature are the work and the span, respectively. Okay? So the work is the total number of steps that it takes to run a program down to a value under the sequential evaluation semantics that we talked about, like way back when, right? The thing we've been doing all week about stepping, counting the number of steps that a program takes is the work. The span is just counting how many parallel steps the program takes according to the parallel stepping relation that we just defined, which, will be less because if I have that example from before, then in one parallel step, we get to 310, right? So that can be less in certain programs. So the idea is that the work measures how many instructions are you doing overall. The span measures what's the length of the longest actual data dependency in evaluating this program. So you can think of the span informally as how long does it take on infinitely many processors, or not infinitely, but unbounded many processors, right? So how long would it take if any time that I possibly could evaluate something in parallel, I do evaluate it in parallel. Okay, but the real thing you want to think of the span is what's the actual data dependence in my program that restricts how parallelizable the algorithm is, right? Because the idea is we're taking our functional programs and we're viewing them as, right, our functional programs written in this language, we're viewing them as parallel programs without really saying much about, notice that we haven't brought up like threads or concurrency or GPUs or something like that yet. We're just saying what parallelism is there in this program. Okay? So that's what the span is measuring. So the idea of cost semantics is that what we're going to do is to annotate our evaluation relation semantics to keep track of the work and the span. Okay, so rather than having, this is just like a technical device. We could have just kept our previous sequential evaluation and parallel evaluation, but rather than doing that like that, we're just going to write one relation that kind of keeps track of what those would have been if we had spelled it out as some number of steps, which is basically just running over the proof of this theorem that we did up there and counting what's going on. Okay? So if, let's just do the key cases. So suppose I want to evaluate E1, E2 to V1, V2. And now what I want to do is I'll write evaluation superscript WS to mean it evaluates with that work and span. So this is kind of like profiling or something like that, because with an execution trace, what we'll do is we'll count two numbers, the work and the span. So suppose that E1 evaluates with work W1 and span S1 to V1, and E2 evaluates with work W2 and span S2 to V2. Then what are the work and span of evaluating the pair E1, E2? Well, what we do is we count how many steps did it take total according to the sequential semantics for the work, and we count how many steps did it take in parallel for the span. So what's the work? W1 plus W2. And what's the span? The maximum of the span 1 and the span 2. Why? If you look at this part of the proof of the theorem, which we didn't do, but admittedly you can kind of imagine how it goes, by induction, right, instead of a bunch of parallel steps, we'll get a bunch of sequential steps. We'll get a bunch of sequential steps there. And then to sequentially step a pair down to a value, if we have E1 going into V1 in N1 steps, then first we do those, because in sequential evaluation, we evaluate the left-hand side first. If we have E2 going to V2 in another N2 steps, then our ultimate chain would take the sum of those steps. Then for the parallel one, it's exactly what we said there, which is I run the two of them in parallel until one of them finishes, and then I run the rest of the other one, and therefore what we get is the bigger of the two. Okay, so the cost semantics for that is just saying that we would have a rule like this, where the work of doing something in parallel is the sum, the span is the max. What about our let over there? Let, what is it? Let x, y equals E1 in E2 evaluates with some work and span to something. Well, what do we do first? First, we evaluate E1 with, let's call it, work 1 and span 1 to a pair of values, V1, V2. And then we evaluate the substitution, V1 plugged in for x, V2 plugged in for y, in E2 down to some value V with, let's call it, work 2 and span 2, and then the overall answer, right? So suppose I have a let. First I run the pair position down to a value. Then I plug in the pieces and run the continuation, the body of the let. And then whatever answer that steps to is the answer that that steps to. Okay. What's the work? Work 1 plus work 2. What's the span? S1 plus S2, because there's no parallelism. And actually, we should have work 1 plus work 2, and span 1 plus span 2. Right? Because we do the pair position, then we take, remember, the actual instruction step that says, oh, sorry, that's not the right thing to point at. It's the rule that's not here, right? Which is the actual reduction step that says let on a pair of values plugs in and goes, right? So that's the 1. And then we have whatever we did there. Okay, yeah?
Does that mean for pairs there's no added cost to constructing the pair?
Yeah, so like if we're counting the number of steps according to the sequential stepping that we've done so far, then remember the rules are a pair of two values is a value, right? Like when I have parentheses around E1, E2, where E1 and E2 are values, that's already a value. So you could have an additional thing. Sometimes you'll differentiate between a pair expression and a pair value, and there's a step for like allocating the pair value. Yeah, so like all of this is meant to kind of just, right, so like you can design your language however you want, and then you can outfit it with a cost semantics depending on what those step rules are, right? So it's not, we're not like committing to what the operational steps are supposed to be here. I'm just doing it for one particular language. Yeah, but yes, it does mean that. That is the choice for this language. Other questions? Yeah. Yeah, so it's a lot more difficult to do this for laziness because the cost semantics isn't quite as clear about when things, it's like because of this issue of it's less clear when things are evaluated. So for that, what you want to look at is maybe the stuff on futures in the chapter after the chapter on this stuff in PFPL, which is maybe a little bit related to that. But yeah, it's a much trickier thing because with laziness there, you're sort of have some effects going on in your operational semantics that sort of aren't happening here. Yeah, so that's a much harder problem to solve. Okay, so now what should we say about this? I guess let's keep that. Yeah, okay. There. Okay, so you get the idea with the annotating the evaluation relation to keep track of the costs, right? So we're just sprinkling stuff there. So what's the theorem that relates this to what we did above? There's a whole bunch of different, like basically the things you would think are true, but let me spell out a few of them. So one thing is that if E evaluates with work W in span S to V, then E steps sequentially in W steps to V, and E steps in parallel with S steps to V. Okay? So remember, we started off by defining a notion of sequential step, like on Monday. We defined a notion of parallel step earlier today. Now we've defined an evaluation relation that's supposed to predict those. So one theorem we would want is that it does in fact predict those in the sense that if E evaluates with our prediction, then it actually takes that number of steps to run it, right? How do you prove this? Well, it's basically that theorem, except you keep track of costs. So for example, in the case where it's a pair E1, E2, right, what we need to know is if this evaluates with work 1 and span 1, and that evaluates with work 2 and span 2, then that evaluates with work 1 plus work 2 and the max of span 1 and span 2. And let's see. So let's just think about the span part, right? The span part says then by induction we get not only does that evaluate in some number of steps, but in particular that evaluates in S steps. And so by induction we get that this chain has length, I guess now it's called S1, and that chain has length S2. And then you argue that, like, we just said this and you believed me before, so hopefully you still do, that that has length max of S1, S2, because we run both of them in lockstep until one of them finishes, and then we just, stand still on the component that finished first. Okay, so that says that. And then we can check that the converse kind of thing holds, which is if E evaluates in W steps sequentially to V, then there exists an S such that E evaluates keeping track of W and S to V. And if E evaluates in parallel with S steps to V, then there exists a W such that E evaluates in WS steps to V. And if E evaluates with WS to V and E evaluates with W prime S prime to V, then W is W prime and S equals S prime. And there's a few more things. Well, let's just stop there. So right, the idea is that what I'm trying to justify is that this notion of evaluation keeping track of costs, right? Evaluation with the work and span is a good way of capturing sequential and parallel evaluation with work S and WS, right? So like we've captured exactly that information. So on the one hand, if we have this, then it actually predicts it. On the other, if it runs like this, then we know that it evaluates like that, right? So this is, the other sides of that theorem. Okay, so now we've got a tight correspondence there that says that we've really said the same thing twice. Okay, good. All right, so, okay. Right, so all we've done now is to sort of start from, well, right, so like why bother connecting these things? Our sequential evaluation was kind of the tool we've been using all week long so far to talk about evaluation. Parallel evaluation was a nice, natural extension of that that says what the parallelism is in a functional program. We've now got a concise representation of all of those two evaluation relations. But so far, this is all at the level of what I started off by calling the abstract costs. We haven't yet hit anything concrete, right? For all we know, W and S are meaningless numbers that have nothing to do with any actual evaluation on any actual machine, right? They're just things we thought to decide to think of in profiling our code. So the question is, what is the action on morphisms that tells us that this abstract cost is preserved down to some concrete cost? What prediction can we make about an actual execution environment based on these numbers that we just, decided to count? Okay? So the idea here is that we would like some sort of theorem that says work and span predict evaluation on some sort of machine. Okay? And the original one of these is something called Brents Theorem, which is due to somebody named Brent in the 70s. And it says something about evaluating arithmetic expressions being compiled to some sort of machine. So in particular, we can think about what's called a shared memory multiprocessor machine, or SMP. Okay? And the idea, the thing to have in mind here, is that what we've got is a machine that has P processors for some parameter P, and each processor has constant time access to some shared memory, right? So there's some memory that's shared between all of the processors that the processors can access in constant time. Constant might be a little ambitious here, so sometimes people will think about log of P time access. So there might be some overhead to accessing the memory, but you can do all of this for that too. And then there's some sort of fetch and add instruction or some other sort of synchronization primitive. And the idea is that fetch and add is a very basic low-level one. You can build other ones out of that. But what that means, if you haven't seen it before, is that in one atomic operation, you can get the value stored at a particular address in memory and add a fixed constant like 1 to it. Okay? And the hardware takes care of synchronization between different processes on the same fetching and adding on the same memory cell. So if two different processes at the same time say, I would like to fetch and add address blah, then those will be serialized in some way. Okay. So what we need to do is to compile our program and to schedule the work in a way that preserves the time bounds in some way. Okay? So the idea with the Brent type theorem, or with the Brent's principle there, so sometimes this gets called a Brent type theorem or a Brent's principle because we're taking something that someone did once upon a time and extending it to lots of different contexts, right? But this idea of a Brent type theorem or a Brent's principle for your language is that the actual abstract cost will predict evaluation on some sort of machine. Okay, so what can we say about work and span specifically? If E evaluates with work W and span S to V, then E can be run to V in time something, right? So like the form of the theorem we're looking for is if we have abstract costs work W and span S, then that makes some prediction about the running time of the program. And when you set up one of these mappings from abstract costs to concrete costs, then what you want to do is you want to think about what features of the target machine do you want to get to come up in the concrete costs that weren't in the abstract costs, right? The whole point of the abstract cost is to abstract away from certain features of the actual concrete machine, right? The idea here is that when we're writing our parallel functional programs, we don't think about how many processors are on the machine, right? When we wrote merge sort on the board before, we didn't write merge sort for a machine with 17 processors or merge sort for a data center with 1,000 processors or something like that. We just wrote merge sort, right? At the level of the abstract cost, we can analyze the work and span for merge sort. So just like, everybody here has done basic algorithm analysis, you compute big O bounds and stuff like that. Now that we've defined the span of a program, you can go through and you can analyze the span of merge sort, just like you analyzed the work of merge sort once upon a time in some intro programming course. And so we can think about the work and span before we ever know how many processors we have to use, right? It's a processor machine independent notion of parallel complexity. Okay? But when we're thinking about, well, I've got my laptop here and it's got 2 cores or 4 cores or whatever, then we want to start to make actual predictions about actual machines with actual physical hardware. Okay? So a good first feature to look at if we're thinking about parallelism is how many processors are on the target machine. Okay? So what we would like is an expression depending on the number of processors that we can predict. Any guesses? Have you seen this before, or did you come up with that on the fly? Okay, nice. And then I'm going to throw a big O in there for a fudge factor, which can, of course, hide arbitrary amounts of, actual slowdown in practice. Okay, so why the max of W over P and S? Okay, let's stop there for a second. Let's parse that. So the suggestion was W over P makes sense because you can get at most a p-fold speed up if you have P processors, right? Suppose I have 2 processors and I have 100 things to do, then it'll take at least 50 steps, right? Because, or it can be done in at most 50 steps because I divide my work into, at each step I do 2 steps instead of 1, right? If I have 3 processors and I have 99 things to do, then I can do it in 33 steps by doing 3 at once. Okay, so I divide my work into chunks of P, right? At each time step, I try to do P things. Why the max of that and the span?
That's the actual amount of parallelism present in your program.
Yeah, the span is the length of the longest actual data dependency necessary to do the computation. So what this is saying is you try to divide it into chunks of P, but you can never beat the span. Okay, so the Brent theorem for this says you try to divide your work into chunks of P, but you can never beat the span. So what this leads to, which I think is really interesting, and this is something that we've integrated into some early functional programming courses at CMU, and now that I've ported them over to Wesleyan, is the idea of sort of parallel algorithm analysis, which means when you're doing your basic functional programming, right, like, maybe once upon a time you had a basic functional programming course and you wrote merge sort and analyzed it and was like, okay, yeah, it's n log n or whatever it's supposed to be. You can analyze not just the work, but you can just as easily, or almost just as easily, the math's sometimes a little harder, analyze the span too. So you can analyze the work and the span of your code. And then the Brent theorem, right, is exactly this arrow that tells you how the abstract costs map to the concrete costs. Okay? So, we'll do things like the span of merge sort is order blah. And actually, I'll let you figure that one out under the hands-on session. But, you'll do an analysis like the span of merge sort is order blah in terms of n, where n is length, as usual, of the input, right? So it's just like all of the kind of asymptotic analysis that you know and love, but you can do it for span in addition for work, right? So it's just the same tools. Once you've got a recurrence, it's just a recurrence. You solve it the same way you solve any other recurrence. You can just think about the work. And so then you can think about, the mode of use of this for developing software is think about how parallelizable an algorithm is. Okay, so when you're designing an algorithm, when you're writing a piece of code, before you ever bring up execution on an SMP, or I'm running on a GPU, or I'm running on a data center, or whatever, you can think about, is this a parallel-friendly piece of code, or is this not a parallel-friendly piece of code? And generally what you try to do is, the thing you hope for, the best case, is you look for something with the same work as a sequential algorithm, but small span. Okay, so if you work on this during the hands-on session, if you analyze the span for merge sort on lists, you'll see that it's actually not very good, which is kind of surprising because merge sort looks like it should be doing kind of a, well, I've got 4 things, and then I've got 2 things, and then, I sort of break down, divide and conquer in half. And so it seems like, if you think about the tree structure of the recursive calls in merge sort, the span should be something like log of the number of things in the list, because how many recursive calls does, it's not still on the board, does merge sort make? It makes one recursive call on each thing in this tree. But remember that that recursive call and that recursive call are in a pair and therefore can be run in parallel, and so on all the way down. So it looks like if you just kind of focus on the overall structure that the span should be log n or something like that. But if you think about it carefully, then there's actually a trick or there's like a gotcha which happens, which means that it's actually going to be much worse than log. Okay? So one thing that you can do during the hands-on session is to look at merge sorting trees instead of merge sorting lists, which is kind of just a fun functional program to write. And the reason that it's a nice, interesting functional program to write in this kind of context is that it does have the same work as a sequential algorithm, but has a much better span. And the idea is that as a data structure, trees give you many more independent sub-pieces to process all at once than lists do, because lists just have a head and a tail, whereas trees kind of come with two sub-pieces. Okay, so that's kind of a hint for just a sketch of how this kind of stuff should be used, is that we've got this abstract notion of cost. We use that to think about, is this a good algorithm or is this a bad algorithm, in the same way that we use asymptotic analysis to think about, is this a good algorithm or is this a bad algorithm. So of course it has the same pros and cons as any kind of big O analysis, right? Like there could be a lot hiding in the constant and it might not work well in practice and stuff like that. But at a high level, it gives you a rough and ready guide of, is this something that I should think about running in parallel? Or is this not something that will work very well in parallel? Okay, but then that's all dependent on this idea of a Brent type theorem, or a functoriality that goes from your abstract costs to your concrete costs, says that your compilation preserves your abstract costs down to your concrete costs. Okay, so let me just sketch a little bit of how this kind of thing gets realized. So this is all in PFPL chapter something, maybe 37, I'm not quite sure. But just to sketch it on the board a little bit, because it kind of leads into various things that'll be happening later in the week. The idea at a high level, okay, so like actually doing this down to an SMP isn't in PFPL, but an idea that sort of gives you the crux of what one would do is, and the idea is that what we'll do is we'll define a machine that consists of states of the form new A1 through AN. So this is what Bob was writing as a signature or a assignable context sigma this morning. A1 maps to S1 together with AN maps to SN. And the idea is that these are names for tasks, right? So in our concrete machine, just like with an SMP machine, we're going to have concrete processes or tasks or something like that we're going to run. And the S's here in our machine are either going to be a closed expression or two new things of the form join A x dot E and join A1, A2, x comma y dot E. Okay, so what do these mean? That means wait for task A to complete, and then plug its value in for x. And that means the same thing, except it means wait for tasks A1 and A2 to complete, and then plug both of their values in for x and y. Okay, so the idea is that A individual process is of a very special form. Either it's a closed expression that you're going to run, or it's waiting for a value from some other task, or it's waiting for a value from two other tasks. Okay? And so we can set up the operational semantics of this as a transition system. And let me give you a flavor for what some of those rules look like. Suppose you have a task which is to evaluate E1 and E2. And let's just suppose that one of E1, E2 is not a value, so there's some actual stuff to do there. Then, what machine state do we want to create? We want to create a machine state in which we have a task running A1, we have E1, we have a task running E2, and our original task, which was trying to run both of them, is waiting for A1 and A2 to complete, and when those come back, it will create the value consisting of whatever came back. Okay? So this is what's sometimes called a fork, because we have one process A that's supposed to run a pair, and we have an idea in mind that pairs are going to be evaluated in parallel. So what happens on our machine is we allocate two fresh tasks. So there's some alpha conversion going on in this new thing that says that these are really bound variables, well, not bound variables, bound assignables, which stand for new names for tasks. Okay, so those are just like the assignables from this morning, which stand for names for tasks. And then we go on with A1 going that, A2 doing that, and A waiting for them both to come back. Okay? And then conversely, suppose we have A1, A2, A, where A1 is running V1 and A2 is running V2, where V1 and V2 are both values. Then what we do is if A is waiting for the results of A1 and A2, x2.e, then what we do is A goes on with life, running V1 for x1, V2 for x2 in E. Okay, so this is sometimes called a join, because what we're saying is that suppose that we spawned off two independent tasks to run E1 and E2, and now at this point they've both finished, and they're both running values, so we have values sitting there for both of them. Then what we do is we activate the person who was waiting for those two and have it go on with its life, knowing the values that were computed. Okay? And then we can do similar things for let. So for example, if you have new A dot, A is trying to run let x equals E1 in E2, then that'll transition to I start off a new process, which is running E1, and A is waiting this time just for the result of A1, and then it'll run x dot, or sorry, then it'll run, let me do the taking apart a parallet that we've been talking about. Then it'll run let x, y be z, where that's the variable bound there, in E2. Okay, which is to say, suppose I have a program that's trying to take apart a pair. One thing it can do, okay, this is maybe gratuitous, and like we should be doing something different for local evaluation, but if we want to sort of uniformly in this machine model any step of evaluation as sort of spawning a new process, what we do is we spawn off one new process, which runs E1, and then when that new process, A1, comes back with a value, we'll plug that into E2. So you could also do like a local machine for doing this local transition, because instead of spawning a new thing, A could have continued the evaluation. But this kind of naturally corresponds, it's just like simplifying the things by using one mechanism. Okay, so what we've got is rules like that. And these rules are actually very similar to, if you look at stuff on stack machines, then what we're doing here is sort of a parallelizable stack machine, because what we're doing here is setting up, here we're kind of pushing something on the stack, and here we're popping the stack. But we've got different tasks doing the different parts. And so then, since I'm running low on time, I won't try to give the rule, but the idea is we have those local transitions which work just on like a little bit of this soup of processes that are running. And the global transition says that at each step you select 1 is less than or equal to k is less than or equal to p tasks to make local transitions. So if we have a big soup of processes like this, we select some number of them to make local transitions. We step them locally, and then each creates or garbage collects processes, right? So note that in the fork rule up there, 2 new tasks came into existence, A1 and A2. In the join rule up there, 2 tasks disappeared. And so there's kind of a global synchronization represented by alpha renaming here, which says that if we have 2 different local processes that spawn off, in total 4 new tasks, then we have to now all agree on the names for those tasks so that we don't get confused and send the values from these over here to this one instead of to that one, et cetera. Okay, so the global synchronization, the fetch and add in the SMP, is showing up when we have independent processes creating tasks which each have new names, A1 and A2, right? Those need to be alpha varied, made unique, so that everybody knows who's talking about what. Okay? And so then that's kind of the idea of a global step. And so then what we can do is we can compile a functional program down to this machine. And then the key issue is scheduling. Scheduling is how do we select which tasks to run? Okay? And there are different algorithms for this. So you can do depth-first scheduling or breadth-first scheduling. And these can have different running time. And also, a key thing to think about is they can have different space usage. Okay, so I know that was a little bit fast, but the big picture is what we've got now is a machine. And the machine is, still very high level, but it captures this idea of we have different tasks running in parallel in a way where we can realize the functional programs on that machine and then schedule. And then you can prove a Brent type theorem that says that this machine actually realizes the abstract costs. Why? Because at each step in a global transition, what you do is you kind of greedily take as up to p steps, right? You can see that in this machine, you're taking up to the number of processor steps you have in each global transition. And so that kind of gets towards the idea of divide the works into chunks of p, but you can never beat the span. Okay? So what we've seen now is that parallelism is something we could talk about over here. And then we can map it to an implementation in terms of some concurrent processes. So the important thing to take away is that parallelism is not concurrency in the same sense that functional programming is not assembly language. Just because you can realize parallelism on some machine with concurrent processes doesn't mean you should equate the two. And the real reason for not equating the two is that you can think at a high level about how parallel your program is by analyzing the work and span. And that gives you information about whether this is a good program or not. And you don't need to compile it down to a specific implementation in order to think about that. So the goal here, and I think this is really like a field where there will be a lot more research in the coming years, is this general template of you have a high-level language with abstract costs that gets preserved down to some implementation and some concrete costs. And what I've tried to suggest to you today is just like one thing you can look at. You can think about machines that can run many things at once, functional programs being mapped to them, right? There's a lot. You could start to think about different features of the target machine, like how much memory you have, or what your memory hierarchy looks like, or how much it costs to communicate between different parts of memory or the outside world or something like that, and then try to think about high-level languages with cost semantics that predict this. Okay? So in terms of making the predictions, this operational semantics says what to do for closed programs, right? So then when you start to think about making predictions, what you really want to do is you want to analyze them in terms of the size of the input, right? So that's not something we've really talked about yet, because the operational semantics is just saying, okay, I've got a closed computation. When I run it, how many steps does it take? Then on top of that, you can build a notion of an analysis that predicts, this is order n in terms of the size of the input. So that's something that we'll be talking about more in the next block of lectures, when Jan Hoffman will be giving some lectures on his tools for automated complexity analysis, which start from this kind of cost semantics for closed programs, and then on top of that, build a notion of how do we automatically compute big O bounds for them. Another place where this kind of stuff will come up later in the summer school is this idea of a soup of communicating processes is exactly this idea of concurrency. And today what I've been arguing is that you don't need to think about soups of communicating processes just in order to think about parallelism, because parallelism is about the data dependency in the computation, not about structuring programs in this form. However, if you want to structure programs in this form, and there's times when you do, then what Alex Nevsky will be talking about in the third block of lectures is logics for reasoning about imperative and concurrent programs and understanding the behavioral correctness of that. Okay? So hopefully you'll be pretty well set up for both of those. OK, so I think I'll stop there. Thank you. Thanks.
So for all the people in this room, there exist for each of you many reasons